We're going to take a look at how to find the domain of some common functions, types of functions that we see all the time. Now, the hardest part about having to do this, besides memorizing how to find the domain, is classifying functions by what type of functions they are, because this is how we're going to start this. So for our first thing, if we're dealing with polynomials. Now remember, polynomials are a group of terms where all the exponents are whole numbers. So stuff that we're kind of used to seeing the most, like x squared plus 5x minus 3. That's a polynomial. More specifically, it's a quadratic, but generically speaking, it's a polynomial. Now, when we're finding the domain of things, remember, domain is the values you're allowed to plug in. So what your idea is there anything I can plug into this machine and break it? And notice you can plug in any number you want, you can square it, it'll give you a number. You can take any number you want, multiply by 5, it'll still give you a number. And you can subtract 6 from all that and it'll still be a number, right? So there's nothing you can do to break a polynomial, which means the domain is all real numbers will work. So the key here is, though, you have to be able to recognize that it is a polynomial. The second common type of function that we've seen so far are something called rational functions. Now remember, a rational function is just a fraction of polynomials. So kind of like a quick example of that would be like x plus 3 over x squared plus 5x minus 1. Something like that, right? A fraction of polynomials. Now the idea here is, can we break this machine? And the answer is yes this time, because since we have a fraction with variables in the denominator, there's a chance that we could be dividing by 0. And we know we're never allowed to divide by 0. So to find the domain of a rational expression, we got to find the values that make the bottom equal to 0 and get rid of them. So there's kind of some steps here. Step 1, set the denominator equal to 0 and solve. Okay, now this is going to tell us all the values that make the denominator 0. Remember, we're not allowed to have those values, so the domain will be all real numbers except the ones found in step 1. Okay, we'll get an example of this in a second. All right, so since with a rational expression we have variables in the denominator, we got to watch out for what makes the bottom 0. So we set the bottom equal to 0 and solve. The domain is going to be, well, everything else, right? All real numbers except for those. Now, the only one other type of function that we've seen so far with these lectures would be radical functions. So functions that have a root or radical in them. So like g of x is the square root of x plus 3 or something along those lines. Well, unfortunately, we just can't classify something as a radical function. We actually have to specify what type of radical it is. And I'll show you here in a second why. Because there's a difference between odd roots and even roots with the rules of what we're allowed to do. So let's start out with odd roots. So what do I mean by that? Like the cubed root, 5th root, 7th root, 8th root. Now the nice thing about odd roots is, think about this. Is there any number we can put into an odd root and not get an answer out? Well, the thing we're normally worried about with radicals is negatives. But as long as the root's odd, you can actually find a value that works, right? Negative 2 times negative 2 is positive 4, times negative 2 is negative 8. So as long as the root is, odd, the number underneath can be positive or negative and it won't break it. And it could be 0, right? The cubed root of 0 would be 0. 0 times 0 times 0 is 0. So if it's an odd root, you can't break it. It works no matter what. So our answer here is all real numbers. However, even roots are a little bit more difficult because we can break an even root, you know, like a square root, fourth root, sixth root. Because if I said, what's the square root of -4? Now, there's no real answer to this. We do know that we can use complex numbers or imaginary numbers to rewrite this as 2i, but we really haven't answered it using real numbers. And when we're talking about domain, up to this point, we're only going to be talking about real numbers we're allowed to use. So since there's no real number that can give me an answer to this, we said that we're not allowed to take the even root of negative numbers. So what we're going to do here is quite a bit like what we did for our rational expression, just a little bit different. So we're going to do 2 steps. Well, 1 really. Set the stuff inside greater I'll go ahead and say it. Greater than or equal to 0 and solve. Now, why are we doing this? By the way, the stuff inside of a radical is called the radicand, but just generically speaking, the stuff on the inside. So if we have some function here and it's an even root, we're going to take all that stuff inside and set it greater than or equal to 0. Because greater than or equal to 0 just means not negative. Because really that's what we're doing. We're just eliminating the negatives. So once you solve, whatever you get, this is the domain. Okay, let's just try a few of these real quick so we can kind of see how they all work. So let's say our directions are find the domain. All right, let's start out with something easy. So let's say we got 4x squared minus 6x cubed plus 7. All right, if you were asked to find the domain of this function, the very first thing you have to do is classify what type of function it is. Well, in our case, that's a polynomial. And we know that the domain for the polynomial, so I'm going to do domain just kind of like this, is all real numbers. Now you can use the symbol there if you want, or you can just say all real numbers, you can write it out. Or you can use interval notation for that. By the way, of course, interval notation would be all the numbers from -infinity to +infinity. All right, that quick and that easy. What if we had something like this? Let's try another function. What if I said g of x was 4x over x squared plus x minus 6? And I said, find the domain. Well, to find the domain of this expression, we got to first say what type it is. So according to the only ones we have, it would be a rational, right? Because it's a fraction of polynomials. Excuse me. So following our steps, we want to set that denominator equal to 0 and solve. Notice we don't care about the numerator. We only care about what's going on the bottom because we're not allowed to have a 0 on the bottom. We set that equal to 0 and solve. In this case, this is a quadratic equation we have to solve. Following all of our steps and kind of skipping a bunch, this will actually factor pretty quick. 2 things multiply together equaling 0. One of those factors has to be a 0. Again, skipping some steps so we're kind of down here at the bottom. We get 2 values here. X is -3 and x is +2. So what is the domain of this? Well, the domain is, well, it's all the numbers except for these guys. So it's all the numbers as long as x is not -3 or x is not +2. You can say that in a sentence as well if you like, all real numbers except -3 and +2. This is somewhat just a shorthand way to write it. Now, if you're going to do interval notation for this, I'm not really showing that. It's a little bit tricky. Think of the number line. It's all the numbers except for -3 and 2, so really it's just looks something like that, right? It's the whole number line, just got 2 holes right there. So you have 3 regions that are shaded. So interval notation is actually -infinity to -3. That's the left. The middle is -3 to 2, and the right is 2 to infinity. So you can see interval notation gets a little messy when we just got to jump over values like that. But the book may be giving it to you in interval notation, so you may have to recognize that. All right, let's try 1 or 2 more here. Gotta get this out of the way. I need some more room. All right. Let's see. Directions are the same. Find the domain. Let's try. Y is equal to the fourth root of x squared minus 9. Okay, so we got to classify it first. So what type of function is this? Well, this is a radical function, so we need to further classify that. Does that have an odd root or an even root? If it has an odd root, you're done. You just say all real numbers. If it has an even root, we got some more work to do. Well, that's the fourth root, so we do have more work to do. That says take the argument, or the radicand, set it greater than or equal to 0, and solve. Now, unfortunately, there's a lot of work to do here. Remember, this falls underneath a polynomial inequality. The way that we solved these is we changed it to an equal sign, solved the equation. Again, I'm factoring here real quick. That's the difference of squares. Setting each factor equal to 0 and solving. Now, I went through that really fast. If you need to slow down and kind of see how we did that to remind yourself, you may want to do that. Now, once we solve the equation, we put those values on a number line. So that would be what? -3, +3. Since our original inequality had the equal sign, these get closed circles. And remember, this breaks our number line up into 3 different regions. So we want to pick test values for each one of these, -4, how about 0 and 4, and plug it into our original inequality and see if it is true or false. This is pretty easy. -4 squared is 16, +16, minus 9, well that's greater than 0, so it's going to be true over here. 0 squared is 0, minus 9 is not bigger than 0, so that's false. And again, when I plug 4 into there, 16 minus 9 is bigger than 0, so that is also true. So what's our domain here? So our domain, well, it's not easy to write. Probably using interval notation here would be best, right? So to describe this region over here, this goes from -infinity to -3. This region over here goes from 3 to infinity. And of course, we're going to put them together. Okay, so what values are we allowed to plug into this original problem? Any value that's from over here smaller than -3, or any value over here that is bigger than 3. So finding the domain of functions, you got to be able to classify what the function is, and then know the steps on how to find the domain from there.